Today we are going to start a 3 or 4 day adventure with chapters 8.5 and 8.6. We're going to be combining information from both sections over these next 3 or 4 days. It will be a fantastic time, I promise. But first, I want to get started with a question. Would you rather receive in 30 days, would you rather receive 30 days from today $1 million or a penny doubled every day? Think about it. Dum, 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 dum. $1 million or a penny doubled every day for 30 days. $1 million or a cent, one little penny, doubled every day for 30 days. There is a correct answer, actually. Well, I mean, either way, if this was a true statement, you would be receiving a lot of money. However, after 30 days, if you chose the $1 million, you would receive $1 million. If you chose the penny doubled every day, you would receive over $5.3 million. So about 5 times as much as you would have if you would have chosen the $1 million. So either way, it's a lot of money, but the penny doubled every day is over $5.3 million because, dun 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 dun, exponential functions. Yes, they're a wonderful thing most of the time. Okay, so to start off this adventure, 3 or 4 day adventure, we're going to start off with a definition. So an exponential growth function is a function in the form a times b to the x, where a is greater than 0, b is greater than 1, and b does not equal 1, obviously, since we don't have our equal to sign right here. Okay? So now, looking at order of operations, our input is now in the exponent. So if we were making a table or some sort using this function, which we will get to in part 2, but just a little FYI, we would first do b to the exponent. Our exponent comes before, then we would do multiplication. So exponent first, then multiplication. Okay? Looking at this table, here if we are increasing by 1 in the x's, the y's are increasing by multiplying by 3 every time. That's the difference between exponential and linear. When we had something that was a line, it was a constant. So over here we have a little picture of a growth. We're constantly getting bigger at a very quick rate. A line was constant, so we would add that same rate. However, here we're multiplying by 3, and that's what gives it this very steep curve. Okay? So here in this graph, it's not this picture. This picture's not that. But looking at this graph, we are looking at the equation y equals 2 times 3 to the x. So if you're looking at a table and you're asked to write the rule for it, notice that your a is your y-intercept. So wherever x equals 0, that y value is going to be your corresponding a. Okay? So a is our y-intercept. Wonderful. Okay. And then our b is our rate that we are growing by. Okay, so the number that we're multiplying by, that we're constantly multiplying by 3, multiplying by 3. If you think of it in terms of where this x is, if you start, say, at 2, and you multiply it times 3 to the 1, which is going to be 3, or 3 squared, which would be 3 times 3, which is 3 squared, so that's your 2. Okay, you're multiplying by that number x amount of times. So you're multiplying it by 3 times 3 times 3 times 3, multiplying it by 4 times 3 times 3 times 3 times 3. Okay, so that x starts to make sense if you think about it in terms of your table and constantly multiplying by 3. Okay, that number that you're multiplying by is your b. Okay, so a is y-intercept, b is our growth rate here. Okay, alright, so let's practice writing rules. Okay, so if we have this lovely table here, and we want to put it in the form y equals a times b to the x. The first thing that's easiest to identify is our y-intercept. So that is our a. So we are going to have y equals, our y-intercept is 8. So we are going to have 8 times our b to the x. We need to figure out what we're growing by. So if we're going from 2 to 4, 2 times what equals 4? That is a 2. 4 to 8, oh, we're also growing by times 2. 8 to 16, times 2 again. 16 to 32, times 2. I'm going with our b is a 2. So we're going to have 8 times 2 to the x. And that is our equation. Y equals 8 times 2 to the x. Hopefully you can read my handwriting. It's a little sloppy, but I think it looks better than it does on the smartboard, so you should be a pro at reading this. Okay. Then over here in this example, we'll just move this a little bit. Okay, again, we're going to go in this form. First thing we can identify is our y-intercept. So we're going to have y equals, our y-intercept is 27 times. Okay, now we need to figure out what we're growing by. So 3 to 9 is times 3. 9 to 27 times 3. 27 to 81 times 3. 81 to 243. If you don't know, math is about patterns. Let's follow this pattern and go with times 3. Check it on your calculator. It is, in fact, 81 times 3. Okay, so this is our growth rate. So that is going to be our b. So we're going to have 27 times 3 to the x. Okay? Piece of cake? Wonderful. That's what I thought. Okay. This is our section 8.6 bit now, which is exponential decay functions. Okay, it's the exact same form. The only thing different now is that b is going to be a positive fraction. Okay, so we're going to be greater than 0 but less than 1. So now our growth rate is going to be in fraction form, which is going to be y is decay. So if you look at this general trend of a decay function, it basically looks like the growth except flip-flopped over, except going the other way. So growth, we were getting bigger. Decay, we're getting smaller. And you read this as far as growth and decay going left to right, just like you read a book. So going left to right, we get smaller here. Our growth, we were getting bigger going left to right. But decay, we're getting smaller. Okay, again, I want you to look at this table. Now, if you're looking at this table, your first instinct, and I know it will be your first instinct, going from 16 to 4 is you want to say, we're dividing by 4. Yay! But looking at the setup of this exponential decay function, when we are taking something to the power of, that's multiplication. So we can't think in terms of dividing by, we have to think in terms of what are you multiplying by. So if we're dividing by 4, division by number is the same thing as multiplication by the reciprocal. Okay, so dividing by 4 is the same thing as multiplying by 1/4. Okay, so here going 4 to 1, we're multiplying by 1/4 again. 1 to 1/4, multiplying by 1/4. And 1/4 to 1/16 is multiplying by 1/4. Okay, those are all equivalent to dividing by 4, but again, we have to think in terms of multiplication. Okay, these letters mean the same thing. Our A again is our y-intercept, so here we're intercepting at 1. There, we have a 1. And our B is our growth rate, which is 1/4, so we have our 1/4 there as well. Okay, well, let's practice. Here, our y-intercept is 1, so far we have y equals 1 times. What are we decaying by? If your first instinct to get from 5 to 1 is to say divided by 5, that is perfectly fine, but dividing by 5, if you look at it as 5 over 1, is the same thing as multiplying by the reciprocal. Reciprocal, we swap our numerator and denominator, so that's going to be multiplying by 1/5. 1 to 1/5 is multiplying by 1/5, and 1/5 to 1/25 is multiplying by 1/5. That is our B. So we're going to have 1/5 to the x. Okay? And this example over here, our y-intercept is 2. So we're going to have y equals 2 times 4 to 2. Yes, it is dividing by 2, but that is the same thing as multiplying by 1/2. 2 to 1/2 is, ooh, that is a lie. That is 2 to 1. I knew when I was making the board there was something strange. That was it. Okay, 2 to 1, and rewind. Let's do this example over again. Alright, looking at this table, yes, our y-intercept is 2. Now, let's check out this rate. Going from 4 to 2 is dividing by 2, but that's also the same thing as multiplying by 1/2. Going 2 to 1, yes, that is multiplying by 1/2, and 1 to 1/2 is multiplying by 1/2, which means our growth rate is 1/2. Now, if I hadn't, if I had the old table on there and didn't fix it, would it have been an exponential decay function? No. No, because it wouldn't have been constant growth rate right here, which you can't see because the eraser. It wouldn't have been a constant growth rate right here, so it would not have been exponential decay, which then wouldn't have fit into this lesson, which is why I had to change the example. Okay? Alright. Here, our job is to tell whether the function is exponential growth or decay, then write a rule. Okay? Alright, so here, reading from left to right, we are getting bigger. So going from left to right, that is telling me right away that this is a exponential growth function. Okay, we are getting bigger as we go from left to right. Okay, now I have to write the rule. Okay, so we know that I'm going to be in y equals a times b to the x form. However, we're not looking at a table anymore. Now we're looking at a graph that we've been given ordered pairs. Okay, the a and b don't change. A is our y-intercept. Are we given our y-intercept? Yes, we are. It is this guy right here. Remember, our y-intercept is wherever x equals 0, or it's where we're intersecting the y-axis, which is, we counted by 2's on this axis, yes, which is 2. I mean, we counted by 2's, which is 10. Okay, so our a is 10 times b to the x. Okay, now we only have one other point, so we can't really see what we are growing by. So what we're going to do is we are going to use this other point as an x and a y, and then we are going to solve for b. Okay, so if we let, let's do this, if we let our x and y, let's make this colorful, make this be our x and y, in green, x, y. Okay, if we let this be our x and y, we're going to plug in. So our y is 12, and then our x is 1. Okay? Now if we solve this problem, b to the first power is b. So we are going to have 10b equals 12. To solve for b, I'm going to divide by 10. So b equals 12 tenths, which is 1.2. Okay? 1.2, yay. Are we done? No. Okay, when we write the equation, we have to have this y and x present. So once we plug in that point to solve for b, we no longer use those numbers. We have used them to find b, perfect, but that 1 and 12 don't appear in my final equation. Instead, I just substitute in my value for a, which I already found, which was the 10, and then I just solve for my b, which is 1.2, to the x. There you have it. Okay? Y equals 10 times 1.2 to the x power. Okay? And last but not least, we are going to do this example. So reading from left to right, if I decide whether it's growth or decay, left to right, it is going down. So this is going to be decay. Okay? Exponential decay. Alright? My y-intercept is going to be 8. So right now I have y equals 8 times b to the x. Okay, again, we are going to substitute in our x and y to solve for b. Okay, so my y is 4, and then times b, and my x is 1. Okay? Alright, solving this problem, b to the first power is b, so I'm going to have 8b equals 4. Divide by 8. 4/8 is 1/2, or 0.5. Okay, and that's my b. So now I come to my final equation. This y and this x have to be present. So my final equation is y equals 8 times 0.5 bx. If you part fractions more, you can write it like this. Either way is acceptable. That's the decimal right here. Okay, notice, before I'm done, our decay has a b that is a fraction in between 0 and 1, and our growth has a b that is greater than 1. That is checked out. Awesome. And there you go. That is part 1 of our exponential function saga.